we're going to start taking a look at what we call polar functions. Now, polar functions are vectors. They have direction and they have magnitude. So the first thing what is a polar function is that it is a vector. In other words, it has length or magnitude and direction. Okay? And it's very easy to tell polar functions. Now, polar functions have an origin. They start an origin. So basically you have a starting place. And you always are going to start at the origin of something. And we measure its direction by an angle. So we start at the origin and we measure by angles. So if I think of the x-axis or the x and y coordinate system right here, I start at the origin. And from the x-axis, I measure a certain angle, theta. And from that angle, if I go out a certain direction, we'll call that A. This is what we get is a polar function. So this has direction and it has length, or r, like our resultant vector. So how we write polars is very easy to do. A polar coordinate, very simple, is just this. Given an angle measured from the x-axis, given an angle, theta, where we're stopping to, or a radius, we're going to talk about this in a second, a radius, we can get a polar coordinate. So polar coordinates have length, r, and direction. I shouldn't call that a vector though. There we go. Have length and direction. And this is what we call polar. We call it r because it's a radius. Because if you imagine going fully around a circle, we can go around 2 pi or 360 degrees. And these are polar coordinates. Now this should look familiar. We saw these with vectors. Okay? So how do we plot polars? Very simple. We have a special graph. It's called a polar graph. Although I'm not a big fan of polar graphs, but we can use these to help us. I want to plot the function r is 3, my radius is 3, and my direction is 5 pi over 6. So I start with the direction. I'm facing 5 pi over 6. So starting at the origin, I'm facing 5 pi over 6. There it is. So what that means is, if I'm like standing up top here, I'm turning around until I'm facing 5 pi over 6. So this is the face. This is my direction. And then I'm going to move my direction, which is 3 radiuses or radians. And that's where we get the idea, remember, of a radian. It's how many radiuses we are. So if I face 5 pi over 6, I'm going to move out 3 radii away. 1, 2, 3. And that's where we're at. And we're going to put a B right there. So take a look here. Same idea. My direction is 5 pi over 4. But I'm going to move negative 2 radii. I should say radiuses. That sounds kind of weird. Radii or radians. Now this is very important for us. So this says I face 5 pi over 4. Well, 5 pi over 4 is going to put us in the third quadrant. So here it is right here, 5 pi over 4. It puts us in the third quadrant. So I'm facing 5 pi over 4. But be careful, the negative tells me I'm going backwards. So instead of going forward 5 pi over 4, I go backwards 2 units. 1, 2. And that's where point C will be. So it's actually at pi over 4, which is kind of neat because I could also write this as direction pi over 4 and positive 2. So a lot of times with polar functions, we can write them in different ways given their, because of direction. So let's try 3. I'm facing 7 pi over 2. Whoa, not on my graph. So where is 7 pi over 2? So to get the direction on this one, hopefully remember from the beginning of the year, if I take 7 pi over 2 minus 2 pi, because I'm going to go ahead and do reference angles, That becomes 4 over, no, wait, 2, 4, yep, 4 over 2. We get 3 pi over 2. So there's my direction, and I'm going to move 3 radii, or radians. So I face 3 pi over 2, so I'm facing it, and I move forward. 1, 2, 3, and there's D right there. What I would like you guys to do tonight, and we'll go over this tomorrow, is try the last one here, okay? See if you can do the last one. We'll go over that tomorrow in class. All right, so let's go ahead and go to the back here. All right. Kind of a cool thing to do here. Now, example 1 on the back here, we want to plot this point, 245 degrees. So very easy. Off the x-axis, we measure 45 degrees. Now note, I don't have my unit circle here like I did in the last one. That makes it a little bit easier. I'm going to go out 2 units, and there's point P. It's 2 units away. Now the next part's a little bit harder. It wants 3 representations. So let's go ahead and break this up. 245 degrees. How else could I draw this? Well, I still want to wind up here at point P. So one way I could do this, instead of going positive 45 degrees, I could go counterclockwise. And I wind up at the same place. But the question is, what is this angle going to be? Well, I'm starting at 45 degrees, and I'm just subtracting 360. And that gives me negative 315 degrees. So I could write this as negative 315 degrees, but I'm still going positive 2 units. Now, another way I could do this, and there's lots of ways you can draw these out. 45 degrees. I'm still wanting to wind up at this point here, P, which is 2 units away. So another way I could do it, I could add 180 degrees. So now my theta equals the 45 plus 180 degrees, and that's going to give me 225 degrees. But the only difference is I'm going to get to 225, but be careful, that puts me in quadrant 3. We want to be in quadrant 1. So I change my direction. My direction is negative 2. And there's our answer. So how could I get another one? So another way I could do this, kind of ran out of room here, do apologize for that. 245 degrees. If I draw it out, I want to wind up here still. I could kind of mix the both. Make my direction negative, so subtract 180. So I could subtract 180. So theta would equal 45 minus 180. And that gives me negative, what's that become? 135, is that right? Degrees? So I could get negative 135 degrees, but this time again, I also have to change my direction, make it negative 2. So this is kind of some fun stuff to do to mess around with. These all wind up in the exact same place. So if you want to, what I'd like you to do is go ahead and try number 2. Okay, we're going to take a look at a few more questions. We'll go over that tomorrow. Okay? All right. Now, we have 2 different types of coordinate systems that we're going to talk about. One, we have the traditional, what we call rectangular coordinates. Now, rectangular, these are our standard x, y. Polars, these are our r theta. That's our new ones. We can convert between the two using right triangles. Again, if I think of the x-axis and the y-axis, and I draw out some angle here, theta, we're going to meet at some point x, y. In other words, this distance down here is x, this distance up here is y. So how to convert rectangular to polar? Rectangular to polar? Very easy to do. If I want to go from polar, I want to go from x, y to r theta. Well, the first thing we have to do is get r. R is pretty easy. That's my r. I can use Pythagorean theorem, the square root of x squared plus y squared. Well, how do we get theta? Well, theta is pretty easy to do. It's the opposite and the adjacent. It's our inverse tangent of y over x. I don't know anything more than just draw out my triangle. So if I want to go from polar to rectangular, in other words, r theta to x, y, we actually did this with vectors. How do we get y? Well, if I know theta, if I want y, I know r, right? So y, I get the sine of theta equals y over r. So therefore, we can get y by taking r sine theta. This should look very familiar to us when we did our vectors, the component directions. If I want to get the cosine of theta, that's going to give me my x over r. So x equals r cosine theta. So what I would like you to do, make sure you copy these down, and on the next part, we're going to take a look at a few examples of these. We'll see you then.